Here we have another calorimetry problem. A hot piece of metal is dropped into a calorimeter. Since the water and the calorimeter are colder than the metal begins losing heat to the water in the calorimeter. This causes the metal's temperature to decrease and the water in the calorimeter's temperature to increase. Well, since this is a calorimetry problem, we should use the calorimetry equation, negative Q object, in this case the object is the metal, equals Q water plus Q calorimeter. Now the idea here is to calculate as many of the Q's as possible so that we can solve for the remaining one. We calculate Q using equation 2.3, Q equals mc delta T. So we have to figure out what masses we know, what specific heats we know, and what delta T's we know. Well, we don't know the specific heat of the metal, that's what we're trying to figure out. But we do know mass, specific heat, and delta T for both the water and the calorimeter. So we can start by calculating their Q's. Well, the mass of both the water and the calorimeter are given. The specific heat of the calorimeter is given. You're supposed to have memorized the specific heat of water. So in order to use Q equals mc delta T, all we need to do is figure out delta T. Now, as is the case with all calorimetry problems, the water and the calorimeter are in constant contact throughout the entire experiment. So they start at the same temperature and they end at the same temperature. Therefore, for both the water and the calorimeter, the delta T is the same. It is simply the final temperature, in this case 24.2 degrees Celsius, minus the initial temperature, in this case 22.0 degrees Celsius. When we subtract those two, we get 2.2 degrees Celsius. Now we're ready to calculate Q water and Q calorimeter. Let's start with Q water. We take the mass, 150.0 grams, times the specific heat, 4.184 joules per gram degree Celsius, times the delta T, which we just calculated, 2.2 degrees Celsius. When we multiply all those out, the grams and the degrees Celsius cancel, which is good because the unit joule is the proper unit for heat. And multiplying the numbers works out to 1400 once you take into account the fact that 2.2 has only two significant figures. Now let's do the calorimeter. We take the mass, 5.0 grams, multiply by the specific heat, 1.95 joules per gram degree Celsius, and multiply by delta T, which once again is 2.2 degrees Celsius. Once again, when we multiply through, the units cancel except for joules, and that's good. And the numbers work out to 21 once you realize that 2.2 has only two significant figures. So now we can use the calorimetry equation to determine the Q of the metal. Negative Q object equals Q of the water, 1400 joules, plus Q of the calorimeter, 21 joules. Now when we add these, we get 1421 joules. However, look at the significant figures. 1400 has its last significant figure in the hundreds place. 21 has its last significant figure in the ones place. The least precise number then is 1400, so we can only report our answer to the hundreds place. So our answer is 1400. Since there's a negative in the equation, the Q of the object actually becomes negative 1400. But notice what happened. Q of the calorimeter didn't matter. Why? Well, because of the significant figures involved, the calorimeter simply did not gain enough energy to really matter in the equation. So in this case, we could have gotten the same answer if we had simply ignored the calorimeter. This actually happens every once in a while in a calorimetry experiment. The calorimeter gains so little energy that it simply doesn't matter in the calculation. As a result, some of the calorimetry problems you'll do in this course will simply tell you, ignore the calorimeter. In that case, you can simply assume that Q calorimeter equals 0. Alright, so now I know the Q for the metal. It's negative 1400 joules. Negative because the metal lost energy. I also know the mass of the metal, it was given in the problem, and I can calculate delta T. So I have Q, M, and I can calculate delta T. So the only thing I'm missing in equation 2.3 is the specific heat, so I can solve for it. Calculating delta T isn't so bad. I'm given the initial temperature of the metal. Now remember, the metal starts out a lot hotter than the water in the calorimeter, so its initial temperature is not 22.0 degrees Celsius. It's given. The initial temperature is 151.7 degrees Celsius. What's the final temperature of the metal? Well, once the metal comes into contact with the water and the calorimeter, it begins exchanging energy with them. The energy exchange ends when the temperature of the metal is the same as the temperature of the water and the calorimeter. So the final temperature of the metal is the same as the final temperature of both the water and the calorimeter, 24.2 degrees Celsius. So for the metal, the delta T is the final temperature, 24.2 degrees Celsius, minus the initial temperature, 151.7 degrees Celsius, which is negative 127.5 degrees Celsius. Okay, before we go on, I want to summarize what we've done so far. Using the information given in the problem, I calculated Q for water and Q for the calorimeter. I added them together and took the negative in order to get Q of the metal. All right? I also just figured out the delta T of the metal. So if I summarize, here's what I know about the metal. For the metal, I know that Q equals negative 1400 joules, delta T is negative 127.5 degrees Celsius, and mass is 28.5 grams. Notice that's everything in equation 2.3 except for the specific heat. So I can use algebra to rearrange equation 2.3 and determine the specific heat. When I do that, I find out that specific heat equals Q, negative 1400 joules, divided by both M, 28.5 grams, and delta T, negative 127.5 degrees Celsius. When I work all this out, I get 0.39 joules per gram degree Celsius. I have to limit myself to two significant figures because Q has only two significant figures. So my answer is 0.39 joules per gram degree Celsius. If I look at table 2.1, this is the specific heat of copper.